Our next talk is by Kartik, The Current State of Post-Quantum Cryptography. Over to you, Kartik.
Thank you. Welcome to this presentation and about post-quantum cryptography. And I hope you have coffee because this is going to be dry. Yeah, or caffeine. So the plan for this session is like having a very high-level overview about PQC and understanding some of the terms that goes around like in PQC forums or just people randomly talking about, which we haven't used previously for classical and traditional like cryptography. And sometimes it feels challenging because you're like, oh, that's completely new. But the concept is not new. It's just like the mathematical algorithms and the way you do it is slightly new. And we also will be looking at the appropriate algorithms that we need to choose for the next-gen algorithms. And a little bit of plan for migration, and we'll have some questions and discussions later on. So the main reason why we all have this is the quantum threat. So as people call the quantum crypt apocalypse, and it's going to be here soon, as like that's what people say. We do have quantum computers here for a very long time, and the IBM Condor, which is now the second largest, like second best supercomputer, has 1/1 physical qubits. Although it's not like logical qubits, it cannot really be equivalent to like 1/1 qubit quantum computer. We're getting there, and like it's improving so much. And there's like loads of articles and like blogs going about saying, oh, we have cracked this, we have cracked that. Just 3 days ago, I saw a headline from like a Chinese supercomputer or like manufacturer who said they cracked the soapbox, like the AES rectangular boxes, which goes about and computes things. So apparently something similar to that, they have sort of broken that using D-Wave quantum chips. I don't know what to make of it because the abstract is in English and everything else is in Chinese. So I don't know, like we'll probably have to wait for someone else to go review it and like explain to us what's actually happening. But still, it's not like a completely new thing. So we will be having it quite soon, maybe if not in 5 to 8 years, then definitely within like 10 to 15 years. And we need to be prepared. And as you all know, like stuff takes a while, like everywhere, like the businesses take a while to get adapted to like new things. Debian takes a while to get used to new things, and people take a while to like switch to completely new things. It's outside your comfort zone, and if you don't understand it well enough, people don't want to use it. So it's always good to start as early as we can. So the main problem is that asymmetric cryptography will be broken. Like the asymmetric cryptography, I mean the RSA, the elliptical curve, Diffie-Hellman, Elgamal style, and stuff which are based on like prime factorization or discrete logarithm problems. All those sorts of things will be broken. And like one of the main contenders that you might have heard, like algorithms called Shor's algorithm, Grover's search algorithm, and such. So I'm just going to go very brief overview, just so that you know when someone says Shor, what they are talking about. So it's like an algorithm where it will reduce the prime factorization problem, which for traditional classical computers is going to take exponential time. And it's very hard to break with just normal computers. But if you use this Shor's algorithm on like a quantum computers with sufficient qubits, then it's going to reduce it to polynomial time. And sometimes it's even like just hours, minutes, depending on how, like what you have set your security level to. And especially because of that, RSA and elliptical curve cryptography is at risk. And if you just say, okay, fine, we also have the other issue, which is not so threatening for now, which is the symmetric cryptography. So it will reduce by half. So whenever people say Grover's, they're talking about the symmetric cryptography, like the thing, because the Grover's search algorithm is like an unbounded, unstructured search algorithm, which can utilize quantum computers. And then it's going to like, it gives you a quadratic boost for brute force searches. So just the normal algorithms that you use to search like the keys for AES 256 or like hash algorithms like SHA-512, that will now be like they will be quadratically like faster. So probably it means like root of that, which is about 128. AES 256 will now be equivalent to AES 128, and SHA-512 will be equivalent to SHA-256 if you use Grover's search algorithm. And I don't know if you can see it properly, probably not. But the main takeaway from like this particular slide, it's from a book, which it's there in the citations at the back, is that the RSA algorithm using Shor is, if you have 2050 logical qubits, is going to take 3.58 hours on a quantum computers. Although we don't really have 2000 qubits yet, but that's like a reasonable assumption. And the other one is if you're choosing RSA 2048, then it's going to take 28 hours, and RSA 4096 is going to take 229 hours, which is still like not a lot of time at all. You can easily break it on like if you just use everything you have for a while. And similarly, there's the ECC, which elliptical curve cryptography, which uses the discrete lock problem, and that's going to take about 10 hours if you use the standard key size, like the P256 and X25519 curve. Those sort of things is going to take just over like 10 hours. And then if you're using the highest security level, which is like 521, it's going to take 55 hours. Even though ECC is like slightly newer and much nicer than RSA, unfortunately, because for ECC we use the 256 like more commonly when compared to RSA, where we typically use 2048 or 4096, the ECC will be the first one to go. So everyone made switch to ECC, and now we have to switch over again. Everything else is just the general overview. We can have a look later on. And let me give a brief introduction for the state of PQC. So NIST has finally standardized like 3 algorithms, and there's like a few others which are almost there, like one in like the final draft and few in the final rounds. And what NIST actually wants is to have different mathematical problems for like algorithms based on different mathematical problems. So if you have, if someone finds out, like let's say lattice cryptography is broken, then we should always have like alternative to use it. And that's why they are like doing multiple algorithms for like the same sort of things. And even though we are not there yet completely, we are getting there. And the governments are pushing the guidelines for migration. So if you have been looking at the UK Gov websites or like the NSA websites and like even France, the ones in Europe and like South Korea, like all of them are pushing towards PQC. And some of them have like distant goals. I think NSA said everything in their IT network should be PQC before 2035, which is like way too long, I think, because we're standardizing now. So, but some of the other countries are like typically saying, start doing it now, and we'll see how long it's going to take. So probably in 3 to 4 years. And another good thing is the prototype libraries are now becoming production grade. So most of the things that we were looking at were reference implementations, which were really good to read, really good to audit, and have a look if the mathematical correctness was satisfied and those sorts of things. But it wasn't really good for production use. So like the implementation wasn't really right, and sometimes they had side channel attacks. Sometimes you don't really look at the floating point, like the time it takes for the operations, and sometimes it's not optimized for like other AVX extensions, like different architectures. So you have to be really good to do security and like especially cryptographic algorithms. And luckily now we are almost like, we are starting to do that migration from prototype to production grade. Can we migrate everything to PQC today? No, but we're close enough. So it's not like the previous times where we had to basically say it's not possible, let's like wait for the next 3 months, next 6 months. Now we can have a think about what's happening, because the NIST FIPS standards are published, and some of the drafts are in the final rounds as well, and they are not likely to change that much. So if you start preparing for the sort of things that the standards say, then you're good in line to like comply with most of the things. And let me go back to like a slight brief introduction to like the types of cryptography we have. So when we were talking about the prime factorization, like the RSA algorithms and the discrete logarithm problems, ECC, they are their own distinct type under the cryptography we have. And we also have few others like newer, not newer in the mathematical sense, of course, but using that for cryptography based on lattice. So the ones that got standardized for the general use case is lattice based, and they work on the principle of having like finding the vectors in n-dimensional lattices with errors, like learning with errors and all those sorts of things. If you want, you can have a look. They also have the code-based algorithms, which is actually very old, but wasn't really used much because of its like enormous public key and ciphertext sizes. So this was actually around the same time as RSA, and it has been well reviewed for a very long time. But like the public keys for code-based cryptography are like 1 megs or something, so which is really huge compared to like other sort of cryptography. So we're not using it. But if you have systems that is not really bothered about the size, then we can consider that one. And we also have the hash-based one. One of the algorithms has been selected for FIPS standard. So those three are the ones that you might encounter when you're leading to literature or like blogs and things, just to keep in mind. And there's like lots more like multivariate mathematical problems and like other sort of things, which I haven't really like put here because it's not really a standard yet. And under those sort of subclassifications, we have the lattice-based algorithms, which you can use for encryption as well as like digital signatures. And the ones that got finalized and accepted as a standard was the FIPS 203. It was called as Crystal's Kyber before, and now it has been renamed to MLKEM, which basically means Module Lattice Key Encapsulation Mechanism algorithm. And in a similar sort of field, we have the signature algorithm called dilithium. It was like Crystal's dilithium, and now it has been renamed to MLDSA, Module Lattice Digital Signature Algorithm. And that's like FIPS 204. Both of them have been published and are in the final 3-month review period, where little bit of things can change, but it won't. Mostly, it's like typos and things like that. And the final one, which is for in lattice-based, is the Falcon, and that's still in draft. It's FIPS 206, and they're planning to publish either this year or towards the end of next year. We also have other, like the FIPS 205, which just got published, and it uses like the hash-based approach rather than lattice-based approach. In these sorts of algorithms, the algorithm itself is really secure, and it's as secure as the hash function you use underneath it. So FNDSA is what they call right now, but you have multiple subclassification underneath that, which is like FNDSA for SHAKE256, for SHA, for something else, other hash algorithms. And that one has been accepted as a FIPS standard as well. As for the code-based approach, which I mentioned earlier, which uses like error correcting codes and Hamming distances and those sorts of things. So all of the things are currently in round 4, which is the final sort of thing before it gets accepted. And the main reason why it's not like people are not pushing towards it to be adopted soon is because of its key sizes for the code-based approach. But people are, like many people really want this to be in because it's a completely different sort of style of algorithms, and it has been there in literature, like it has been reviewed for a very long time, as long as like RSA and those sorts of things, when compared to like other lattice-based approaches, which is getting like here maybe 5-10 years or something. And as for the PQCs, we are most definitely going to have to use hybrid PQC for a while, because people don't really trust PQC completely, and it's a new field, and many people, for very good reasons, don't want to switch to a completely new thing, and if it breaks, go back and forth, and like it's a huge mess. So some of the things that you can choose to do is use MLKEM with elliptical curve cryptography for encryption. That's completely safe. And similarly, you can use MLKEM with RSA. It's safe as long as it's separate and all those sort of things. You can also use ML-DSA with RSA signature algorithm or elliptical curve DSA. And you can also use the final or the hash-based DSA with RSA sign. All these sorts of things are acceptable. Of course, it's going to add more sort of issues, as in like the sizes will increase and you will have a lot more to deal with if you're using hybrid rather than just PQC. One of the main things that people talk about is the size comparison between the new PQCs and the old classical traditional algorithms. If you can see there, the RSA and the elliptical curve with 25519 curve, the public key size is like 256 bytes, 32 bytes, and the ciphertext, which is like the signature you would get at the end, is also like very minimal. And both of them fits in a packet. You can send both public cipher at the same time. You can do many things in one packet, assuming packet is like 1,500 bytes, of course. Otherwise, if it's jumbo, then it's probably better. But not everyone uses jumbo packets. But most of the PQC algorithms do not satisfy that. Kyber 768 luckily just about fits in a packet, so you can use it for general purpose encryption and those sorts of things. Dilithium unfortunately does not, and so doesn't like the Falcon or Macaleese, which is still in the draft, both of them. And I haven't mentioned the Sphinx, which is the other FIPS approved one, because it again depends on the hash algorithm underneath it. So there's like very many combinations that you can choose. But even the lowest one doesn't fit in a packet. So that's like some of the things that we need to think about to change the way we write APIs and the codes. Because like you can find many implementations of security tools and like internal business tools and like other things which have like very strict requirements for it to fit in a packet because of the time and like other various different things. And we need to make sure that we know what are these tools, which tools accept these large key sizes. If it affects the entire stack because of using large key sizes, is that a buffer overflow, like many things. And it takes quite a bit of time for us to like go through every single thing and check if it works. So it's always nice to go back, like start now, maybe in 3 years, you know absolutely what are the things that needs to change. And of course, because of the large packet sizes, there's like a bandwidth overhead. So just assume you have like 10 systems in your network, and each of them start sending like huge like public key and like ciphertext to everyone else. It's going to take a lot of your bandwidth without actually giving you anything apart from like what it was giving you before. So many people are a bit like they don't really like it that it has like large packet sizes. But what I would like to argue is like it's not 1960s, it's not 1980s. Like it's now we do worry about the bandwidth, but it's not as much as what we had to worry about previously. So it's just get it over with. Like let's start switching to new algorithms. It can take a little bit of bandwidth, but it's fine. Maybe upgrade your switches and stuff like that if it's really like bothering you. And another thing is the computational like aspects of it. So these sorts of algorithm consumes a bit more like CPU cycles compared to the classical and traditional ones. So you have to make sure that there's like really the good algorithm that you can choose for the thing. So if you're using an IoT device, then you have to really choose, is it worth it to use like a very high security level for its like parameter sets when compared to if you have like a huge server which you don't really mind if it has like large key sizes and if it consumes a lot more clock cycles. And there's also some algorithms that require fast floating point arithmetic. So this was one of the thing I was pointing out earlier. So if you don't implement these sorts of algorithm properly, then there's more issues with like security, like because you can do side channel attacks and like you can check the time it takes and recover keys back. So it needs that, as well as if you don't have fast floating point arithmetic, it takes way slower to do it. So it's a compromise, and you have to choose between the algorithms. And all of this gets even worse if you want to do a hybrid solution, because now you have to do all the classical things and all the quantum things and then like merge it together, and now you have a huge like bandwidth overhead, if you're huge like computational overhead and stuff like that. As for the libraries that we use for prototyping, so one of the really good ones are the liboqs. So this has been maintained by Microsoft and like loads of other companies as well, who go through the reference implementations from NIST and like combine them in a single library package. So you just use liboqs, and then you have all the different PQC algorithms and other things that you can test with just one sort of library to use. But obviously, it is for prototyping. So it explicitly mentions that you are not supposed to use it for production. But it also gives you like the OpenSSL3 liboqs provider if you want to try out as like a Docker container where they merge all these post-quantum algorithms in OpenSSL and give you the Docker container to play around with. Like, how does the public key look like? How do you do key signing? How do you do everything else? Just for prototyping, of course. But now the liboqs has been like sort of taken like they're migrating towards like a production approach, and they call it PQ code package. It's now under like Linux Foundation umbrella, and they're productionizing the liboqs library into like a really good, really audited approach for PQC. And we also have like Bouncy Castle for Java folks. And if you just want to review the implementation, or if you just want to play around with the prototype implementations, then the NIST submissions are really good. Like, you wouldn't expect cryptographers to write that good code. It's like really human readable, and you can go through each line and understand what's going on, which is really nice. So if you just want to learn more, you can just always go through their reference implementations. And how can you help? Which is like the thing, it always sucks because we use these sorts of algorithms and asymmetric keys everywhere, and it's quite hard for one person to know where everything else is. And like, like some people in your team is using something else, and like someone else uses something else altogether. So there has to be places, or maybe like forums and like mailing lists, for us to start discussing the sort of impact it would have. Like, we have to start thinking, oh, what all would it affect? Would it affect the new maintainers, of course? Would it affect the way we release new packages? Would it affect the way we SSH into stuff? Would it also affect the mirrors like that's scattered around the world? How much of it will fail? How much of it needs to like get upgraded to the latest sort of algorithms and those sorts? Like, it's very hard for one person to think about it, of course. So we need to start having a place, a forum to do those sorts of discussions for the near future. And of course, we would need a hybrid solution. I think we do, but obviously if people are comfortable with using PQC directly, then might as well just switch to that without the overhead of switching again and again. But even for hybrid, we need to think about what sorts of hybrid you want to do. Like, do you want like very high spec for both PQC and classical, or would you rather go with like decent enough for both of them so that you don't really have that much of overhead? And there's also things like the certificates, which people usually like tend to forget until it's like very late. But these are also the things that needs to change quite like in the near future. If people are accessing Debian websites, then maybe we should have TLS 1.3 with PQC rather than like just the standard classical algorithms. And like those sort of things, and maybe we have certificates for deploying things, logging into different systems. We'll have to start thinking about why, where, how we are going to change all of those things. Also, the final one, like it's a bit hard. I don't know if anyone has any ideas for that, is how do we preserve our web of trust? Because like Debian developers are really paranoid about security, really good thing. But it also like starts affecting if the entire classical algorithms goes bust, and now like the 20, 30 years of web of trust is like no more. So we have to start thinking about how we are going to either preserve the web of trust and migrate it to PQC, or do we start all over again? Because we know nowadays it's not that hard to meet people, even like either in real life or maybe I was hearing like a discussion over mailing list where people wanted to do the key signing or video call or something. And if you know them like for a brief like months or like years, then maybe they are doing good for Debian, and their key could be signed, those sorts of things. So we have to start thinking about the web of trust. We have to start thinking about what we are going to do with the current web of trust and for PQC. And another thing is start testing out your favorite tools. Like maybe you use a tool that you don't even know has PQC. And because right now is the time to start beta testing, it'll break in pieces, of course. But you have to start submitting issues and other bugs, or maybe if you can solve it, amazing. All that needs to happen starting now. And an example, of course, is the TLS 1.3. So Cloudflare supports TLS 1.3, and your Chrome browser does support that as well. So if you go to the website from Cloudflare, you can check if it has TLS 1.3 and using PQC in the backend. And the Firefox, I think the beta and one of the nightly builds from about February or January, 2024, does support TLS 1.3 with PQC, but it's not really there in the standard Firefox build. But yeah, there's loads of other things that have PQC that you might not know about, like OpenSSH 9.9, which is now in Trixie, has support for hybrid PQC. So you just have to enable it with the flag if you to force it to choose that algorithm, but it's there. So I don't know if it's sorry about that. I don't know if the makefile requires it to be built with MLKEM-S, because that was there before this, but it's you can have a look and check if it's supported for you. I did test with portable version last week, and it worked. The libOQS provider has OpenSSL. The OpenSSL 3 is so much better than OpenSSL 2, but this one still has the same documentation issues, and it takes a while to figure out what's happening and how to choose different algorithms and those sorts of things. So maybe you can start playing around with the libOQS provider Docker container and just testing with your traditional keys, traditional certificates, and PQC at the same time. And if you're a large organization and if you can sponsor, then please try sponsoring the open source implementations. So in your favorite language for security audits, or maybe just mathematical correctness and those sorts of things. Because now it's fairly we have most of the mathematical correctness has been audited. Otherwise, NIST wouldn't have finalized it at all. But the implementation side is quite hard as well. So cryptographers or security engineers who have knowledge of how to do that would probably be really nice for them to go fix issues in crypto libraries and just help around from the scratch. And these are the sort of references and citations that you have. The slides will be uploaded. So if you have any questions, I'm happy to answer.
So we hear a lot about quantum computing breaking cryptography algorithms. Are there new algorithms that run only on quantum computers to do new cryptography things?
So there's loads of new algorithms that are popping up with things, but it's not as I just recently read a paper which has something like quantum AI or machine learning using quantum algorithms, those sorts of things. It does help quite a bit, I guess, and it also helps in having the smaller amount of physical qubits for equivalent logical qubits. So it probably helps in those sorts of error, reducing the amount of error for the logical qubit. But I don't know if there's anything else that can do that. But of course, if you just want to play fight fire with fire, there's quantum key distribution. But it's definitely not for everyone. It's expensive. It's not for day-to-day use, and it's quite a challenge for everyone to start using that. So we cannot recommend for general use cases.
Thanks.
So there's a lot going on here. I think we need somewhere to collect all the information. You've got these excellent slides which have some very good information about software and algorithms and all the rest of it. Maybe some of this Is any of this on the Debian wiki yet? Could we put it there?
It's not there yet, but I'm happy to like add it there.
That would be awesome. And then we could like augment that wiki with a list of all the stuff we need to fix and the questions we have and what the answers might be. That would be great. And I had a follow-up question, which is like a detail. This PQC algorithms library from the Linux Foundation, is that in Trixie yet?
It's not completely finalized yet because what they're doing is they're picking pieces of code from libocus, migrating it to the working group, and then it has to stay there for a while before they are happy with it. So it's still in like a really work in progress, I would say. So it keeps changing. So it's not there in Trixie yet. Maybe we'll have it in like 6 months, 8 months, I think.
Okay, well then it's probably missing Trixie, is it?
Yeah, probably.
Yeah, right. Okay, thank you.
Does this mean we have new advice if we all need to get new keys or something? There's presumably some bottom lines for this, for those of us who know nothing about crypto, but like do X, otherwise it'll all go wrong in a couple of years.
Yes, so I think we might need to start like generating new keys and hopefully signing them with our old keys before this quantum computers like are widespread, so that you can at least preserve some sort of security thing saying, okay, it was there on 2024 where we didn't have quantum computers, so it's probably safe. But of course, that's one of the questions. Do we keep it or do we just throw away all our old keys, start with like a new, either hybrid or like just PQC keys going forwards?
Yeah, I didn't understand that hybrid bit either. Maybe could
So
you
the,
say that
the
again? Maybe I wasn't
hybrid,
listening.
there's few. So the way it would work is you would have both classical key as well as a quantum key, and you just do the same thing twice. So if you're signing something, you say, I'm going to sign it with my classical traditional key, I'm going to sign it with PQC key, and then depending on the other guy, they can either choose to check just one, like, okay, I have the PQC, so I'm just going to check one. But if they're like paranoid, they can check, I want to do both A and B.
So I thought that the hybrid would be do A and then B afterwards, but it's both at the same time, so you can pick and choose.
It depends on what you want to do. Like for example, the OpenSSH one, it says it's hybrid, but it uses like the MLKEM in ephemeral mode as well as your X25519 elliptical curve thing. So in one of the session, it generates like a public key and then shares that along with your normal LGML style ECDH, goes there. That guy checks it back and then computes if it's valid and then sends the data back. So it's using like combined hybrid approach, but there's also other ones if you want to do it like completely separately, of course. You could do it twice if you choose to do it. So I think that's it for today. And if you have any questions, feel free to like ping me on IRC or like email me at my email address.